Well, actually, yeah, I'm talking to you from Australia, so it's actually the afternoon here. Um, the um, the previous talk leads very nicely into the talk that I'm about to give on our TRS project in round 4, and the title was Sustainable Power Delivery Structures for High Renewables. And I'm not going to say too much about the management structure, but we had 4 teams. We had a networks team, a smart loads team, an information networks team, and a grid control team, all led respectively by renowned leaders. Some of you will know Professor Hui from Hong Kong U in power electronics, Professor Victor Lee in information networks, and Professor Chu from Hong Kong UST in control. And the basic parameters of our project were the timing, round 4, 2015 to 19. As I've just said, the main partners were Hong Kong U and UST, but we also had Hong Kong Poly U with Xu Zhao, who just spoke, Imperial College London, and the University of Sydney as external partners. Our budget was just over 47 million Hong Kong dollars. And this is a systems engineering. It complements the previous project, which was more physics and chemistry based. Ours was the system, how the system can work better with high renewables. So most of the budget went to postdocs and students, but we also had a microgrid laboratory, somewhat more targeted to our specific algorithms. So the flow of my talk will be some motivation, similar to what we presented at the beginning, and then the grand challenge briefly, the key ideas and some outcomes, and then a more general statement of outcomes. The motivation is very similar to the previous project. Hong Kong and southern China has an urgent pollution problem, and the globe has an urgent climate change problem. So we were highly motivated to bring systems, electronic technologies and systems engineering to the solution of this problem. And we were motivated by global aspects and some local discussions at the time about the future of Hong Kong's energy mix. Now, putting high renewables into existing grids is causing enormous difficulties. It's kind of like round peg in square hole. So we were also motivated by overcoming a lot of the problems that were appearing in grids that had already started to take up higher renewables, particularly in Europe, but also to some extent in Australia. The problem there was that they're using an old balancing and control paradigm. Basically, the delivery structures developed since the 1880s were becoming quickly obsolete. Since those days, the situation in countries like Australia has become far more dire. And let me just illustrate power flows first before I comment more on that. The traditional grid is based on one-way power flow from large fossil fuel-fired or nuclear generators through transmission distribution to consumers. In the new era, we have largely solar uptake rooftop. Australia currently has the highest in the world in percentage, and you have wind power coming in at where it's sub-transmission, and there can be large wind and or solar farms in generation. The new concept for generators in some countries is now what we call renewable energy zones. So a collection of renewable energy farms is replacing fossil fuel plants. This is really difficult to deal with from a control point of view with the old paradigms. In fact, in South Australia recently, they are getting negative load in the middle of the day simply because of all the solar uptake. So the more the previous peakers are successful, the more difficulties the people running grids have with the so-called duck curve and negative minimum loads and so on. So we're addressing those problems. Those problems are dealt with in 2 major balancing acts. One relates to keeping the system frequency. The common analogy for that is a bit like the cruise control in your car, that it keeps a constant speed no matter what the profile of the road is. Roughly the same kind of story works in a power grid to keep the frequency constant. The other is a bit less easy to appreciate for non-electrical engineers, but it's the balancing of reactive power to keep voltages constant. And if that doesn't work, you can get major collapses. Okay, so our grand challenge, to add a little bit to the motivation, here's South Australia on a certain day where the red curve is the demand and the blue curve is the wind power. So obviously they don't match. How do we have so much renewables and match the existing load? So that's the grand challenge. Renewable power linked to nature is variable, it's uncontrollable, and only predictable with some uncertainty. So this was the question we put to the RGC: how to increase renewable power substantially and simultaneously achieve power balancing, system stability. That's a little bit harder to appreciate. The balancing act is power balance, ramping. Well, you need energy, power, and ramping all to balance. But these systems are also big dynamic systems. And when you start taking out the usual fossil fuel plants, you get a whole lot of new dynamics. And we have to ask, are those dynamics stable? Are the systems secure in the usual ways? So our program is based on a new control paradigm and a new delivery structure. So the key ideas are to make use of, you hear more of these things than what you did at the beginning of our project, but was to think of a paradigm of demand following generation. In other words, instead of the previous paradigm, which was the generation could follow the demand, we have to turn that around to some extent and have demand response and energy storage to bridge the gap between that red and blue curve that I just showed you. So here's a picture for demand response. The red curve is something that can be achieved by modifying the native load, which is shown in black. And of course, energy storage can be represented by a big battery near a wind farm. How to schedule demand response and energy storage in any kind of grid, from a microgrid to a national grid, is a gigantic control and optimization problem with millions of agents. So our work is based on how you simplify these algorithms and get lots of agents of demand response and or battery storage working together to solve the grand challenge. We did this with, I think, a somewhat unique level of integration with the disciplines. We had the disciplines of decision and control, information and communication, power systems, and power electronics with a high-level leader in each area. And our management structure was not to divide the money up and let these people, each group, solve some problems. We adopted a highly integrated approach with meetings and seminars and workshops and students and postdocs that worked between multidisciplinary projects to make sure that we got all four of these areas integrated into the one framework to solve this problem. And the key concepts, which I'll say a little bit more about, were electric springs, which is our name for a special smart load technology, and then distributed control or granular control as a way to pull all these agents together, and then the information technology to create the communications. So electric springs, I can't go into details, but this was a basic idea established by Professor Hoy before the project. And basically it came about because my predecessor at Hong Kong U, Felix Wu, challenged him to come up with a new device that could deal with the variability of renewable power. But it turns out, so it's somewhat analogous to, it is analogous actually, its first version, to Hooke's law in mechanical springs. So the load sharing is a little bit like, analogously to how a mattress holds up, you know, us when we're in bed. Each spring adapts to its own little job. So it's a pretty clever device. But throughout our project, many new versions of the electric spring were developed so that they could take care of voltage control, frequency control, and balancing, and fault ride through. And so these springs became I think of a kind of almost like a generic local controller for the smart grid. Okay, the distributed granular control, I'll just say a little bit. The whole idea here was that instead of the control being in its previous form quite compartmentalized at high voltage, mid voltage, and low voltage, we think of the control task as end-to-end from generator to load, and the control is much more flexible. It can shift basically from kilowatts to gigawatts through the grid. So that's I'll illustrate the idea a little bit more later, but it's based on distributed energy resources in much more flexible control structures. So that's where the control theory came in, and the information technology, but also the electric springs are there at the lower levels. And we, Victor Lee's team invented a new device for power flow control called the power flow router, which played a role in the middle of this scheme. And these things all come together to give a much more flexible control structure. So we envisage a future grid structure with the legacy core grid, and then a whole lot of new clusters, which can be called microgrids, virtual power plants, battery energy storage, renewable energy zones, and with all these new technologies playing a role. Okay, the specific technologies we came up with, I can only give a little taste here. We did a lot of quite basic work on how the structure of grids influences their capability to host renewables, their capability for stability, and so on. We kind of renamed, for the scientific world, we call this power network science, and I'll illustrate it later. In the electric spring area, there was a lot of technological development around AC and DC grids and how the springs can work for voltage and frequency control capability, fault ride through, etc. I encourage you to watch the video that was put together on how electric springs can work across a large area of the grid. The part of the TRS that I led was based around these distributed control algorithms for implementing all the different demand response, voltage control, frequency control, how energy storage is coordinated, electric vehicles are charged and discharged to help the grid, how we can integrate wind power offshore, onshore, solar integration. And then we did a lot of work on restoration and the new topics of resilience and flexibility for grids, which are now hot topics. Something that emerged out of the project that was less part of the proposal was the importance of data-based methods. We did quite a lot of work on networked microgrids, and then these power flow routers that I mentioned, and Victor Lee had another contribution in vehicular networks, which was basically where the battery carrying cars can transport power around in a road network where the cars are charged with electromagnetically. Okay, just to illustrate, here's one, I can only mention a few things, but one paper that was a collaboration between myself and Ron Hoy, where we put electric springs through a grid where there was high renewable power, and the voltages, of course, are upset by that renewable power. But by using our consensus control algorithms and the nature of the electric springs, we're able to turn the voltage from the blue curve here into the red curve there at critical buses. Other work was on a lot of work on electric springs and other technologies and how they can work in microgrids. We had a major microgrid facility which was oriented to our own new technologies. And then, but coming back to the science of the topic, I presented this result at an invited workshop in Cambridge University at the beginning of last year. And I think it's the only time in my career that I've heard gasps in the audience. This is a theoretical result by one of our students at the time, Songya, and myself and Tao Lu, who you'll meet soon. It showed that if you take the existing distribution structure and start extending it into longer feeders, and if you have smart loads here, meaning dynamic smart loads, the system has a major stability problem. This graph just shows that at a certain point, the system becomes unstable. It turned out that Ron Hoy's group had been building cascaded electric springs and noticed that the stability got worse as you cascaded more. And also in a major IEEE working group, they encountered a similar phenomenon in their simulations, but they couldn't explain it. They thought it was something to do with new dynamics. What our results showed is it's quite simply due to the structure. The structure doesn't work. So that's quite I think one of the most interesting results of power system stability that recently. Okay, so overall, the outcomes of the project is, I think the Hong Kong U group is a world leader in power systems and power technologies, and that's just evidenced by the sort of invitations we get for plenary speeches. I was just invited by MIT to submit to a journal. Maria Illich at MIT has invited me to partner her in a major statement on the future research that's needed in the power systems area. We get Ron Hoy, myself, and others in the team get frequent plenary invitations, somewhat mucked up recently by COVID, but anyway. We also feel that we can, with all the training that we've achieved, all the graduate students, that we can achieve a research window for mainland China. And we can contribute. Some of our team members are already involved in major projects in China on wind power and related things, because there's a lot of renewable power developed there. The commercial development, we have some patents and we've had testing by power utilities, mainly in southern China. But our technology is unapologetically out in front, I think, and I think we're confident that we will have increasing commercial outcomes from our work. And also the microgrid facility that was built is there as a resource for the future. I mentioned a major point of our research was collaboration. So I just give some stats on that. Coincidentally, we had nearly 300 journal papers, 300 papers as well as the previous speakers. We had 17 between teams. We had 18 with Imperial College, 12 with Sydney Uni, 62 with universities in mainland China, and 59 with other countries, making a total of nearly 300 papers. So in conclusion, we were motivated by pollution and climate change. We were addressing a big scientific question in the area for a new structure. The old structures are not going to work, and we've seen further evidence of that going all the way down to our distribution structures. So we need new structures. We set up a unique team with an integrated approach between power electronics, power systems, control, information, and communication, and we feel that was very successful. We've developed a number of integrated technologies for the smart grid, and well, we hope anyway that it can lead to changed policies and make the road forward to high renewable systems more achievable. Okay, so the final slide is to say thank you to a lot of people. First of all, we're very grateful to the RGC for funding us, our universities for their support, our researchers, our PhD students, and our industry advisors and the audience today. it's hard in a few slides to capture the atmosphere of a major project like this. And you know, we had lots of seminars, we had lots of workshops, we developed this microgrid lab, and we formed a lot of good collaborations and teamwork. So we're very grateful for that opportunity. Thank you.
Well, actually, I already saw one question from the audience. Hong Kong is a very special city, which has a large population, but limited space. So what are the prospects of the high renewable power in Hong Kong?
Okay, that's a very good question. I've seen studies which show that there's enough roof space in Hong Kong to maybe generate like 15% of the energy. Of course, Hong Kong lacks large open flat spaces for solar farms and wind farms, but offshore wind is surely a prospect. And I know CLP and Hong Kong Electric had plans to test that. And of course, Hong Kong's connected to southern China, where and the future fuel mix of Hong Kong is surely not going to stay the way it is now, as you get the Greater Bay Area. So I think the contribution of research like this can be seen more in the context of southern China and Hong Kong than just Hong Kong. But finally, I'd like to point out that you don't have to build high buildings the way Hong Kong does. I was in Guangzhou a couple of years ago and looked out the window at an amazing building called the Pearl River Tower, which actually is a high-rise building with inbuilt vertical turbines and solar and batteries and so on. And it generates enough power to actually put power back into the grid. So, you know, there are different, you don't have to just have big open flat spaces. We've got the water and we've got the prospect of making buildings different to the way we have in the past.
Thank you, Professor.
And I could add, by the way, that in my home country, Australia, the uptake of renewables is basically in spite of the government. It's just people are putting solar on their roof at an amazing pace, and they're basically putting the old system out of business. So, you know, governments need to stay ahead of the pace here. I can't reflect on Hong Kong in that situation, but it's been quite a shock in Australia, the extent to which people just went ahead and did it anyway. And I mean business and households, and the government's playing catch up.
There's another question from the audience. One of the key issues of renewable generation is that it is less controllable than traditional generation. Then can we really operate a power system without dispatchable power backup to the reliable renewable power?
Simple answer is yes. Yeah, it's obviously it gets a bit more difficult, and you need it just depends. You just need batteries, you need way to store energy, you need some flexibility in demand, and it's a control issue, and I'm fully confident that it's possible. So this comes up in popular debate all the time. Oh, we need dispatchable power, but what you actually need is control, and control can take different forms.
Another question from the audience is that, as Professor Hill just mentioned, renewable energy will bring a lot of new challenges for operating modern power system. Then can we really operate a high renewable grade with the same reliability as the traditional grades?
Oh, yes. The problem is operating the renewables with the old grid. That's the problem. If you change the grid and you change the control paradigm to match the renewables, then I think the problem goes away. And my current job, well, not my current job is still at Hong Kong U until the 31st of December. But from the 1st of January, I'm part of a 300 million Australian dollar project which is basically aimed at solving that problem. And it's very customer oriented, very, very customer oriented. The traditional power system treats customers as passive people that will never complain. But if you get customers engaged with in the value stack around their own power use and generation, and empower them and get retailers offering them things that they'll take up, you can have a whole new world. And I think like places like California, Denmark, and so on, they're way ahead, and Australia is now kind of following on pretty closely with that. And there's no reason why it'll be different in different places, but I believe it's possible. You can't just do it with the old. You can't just put all these renewables onto the old structure, though.
You mentioned demand response. Then how practical the project can implement demand response idea in Hong Kong or in other places?
Well, CLP already had. Yeah, I remember when I was there, I was part of an advisory panel for advanced metering infrastructure, and they were talking about, like, for instance, you have different tariff systems to encourage people to use power at different times of the day. You can have peak power pricing, like when, you know, to reward people for turning an air conditioner off. Those things look very promising. People will shift their load if they see that they're getting a benefit, and also I've even heard that people will shift their load if they get no financial benefit. They just, in Denmark, people just buy into the idea that they're helping the planet. They're making the air cleaner. There's not just monetary reward. You can get a culture around the idea of a cleaner planet or cleaner air where you live.